videos, we have gone over double number lines and tape diagrams and ratio tables. Today, we are going to continue reviewing those as well as graphs. So, the first thing we want you to do is review a double number line. It says a tree grows at a constant rate of 3 feet per year. Write a ratio to represent the amount of growth in feet for the number of months. Then use that information to create a double number line that describes the growth of the tree every 12 months for 48 months. So you're just finishing the double number line. Any questions? Okay, you have about 2, maybe 3 minutes to answer number 2 and number 1. Go for it. All right, so we just talked about it out loud. We were thinking out loud together, and we said if it is 3 feet for 1 year, what do we know about 1 year? It's the same as 12 months, yes? So if they want to know for the number of months, I can say 3 feet for 12 months, because that is the same thing as a year. Make sense? Okay, so what am I completing for 12 months? What would I put above that? 3. So going to 24, what would I put above that? 36? And 48? 12. If we wanted to complete the number line and label every interval, how many intervals are there between 0 and 12?
4.
1, 2, 3. There's 3 intervals, yes?
Yes.
Or 3 units. So what would I put on the first one after 0? No, there's 3 of them, so if I'm doing 3 somethings to get to 12, 3 whats make 12? 4. 3 4s make 12, so this would be 4, and this would be 8. Does that make sense?
Yes.
And 3 whats make 3? 3 1s. So 1, 2, 3. So what am I counting by on my top number line? And what am I counting by on my bottom number line? 4s. So 1s and 4s. So this would be 4, 5, 7, 8, 10, 11. Yes?
Yes.
And this would be 16, 20, 28, 32, and 40, 44. So we have finished our double number line for any month out of those 48 months. If I asked you how many feet did it grow in 22 months, what would you tell me? 20 months. 5, yes? So now I can answer a lot of questions about its growth in 48 months. Does that make sense? All right, next page. Yes?
What if for number 1 you put the 3 in for months, but you also put 1 4 foot for every 1 month?
Perfect. You just simplified it.
Okay, we're on page 224, but we got some good news for you. You guys get to cross out all this. We're not actually going to cut all these rectangles. Okay? On number 3, we are going to do this. So you're going to complete each table. Write the ratios in fractional form, comparing the length of the short side to the length of the long side. So we got 2 parts. We're going to complete the table and writing it in fractional form. So just to make sure everybody understands how to do this, I said I want short side to long side, yes? Yes. So that means the short side is my numerator. So 2, the long side is my denominator, and then we always simplify. Remember to check your 4 key numbers, 2, 3, 5, 7. Can I simplify 2/5? No. I'm going to give you guys a second one just to make sure everybody understands. So my second one is going to be 4 over 10. Can I simplify that?
Yes.
Yes, I can divide both those by 2. Gives me 2/5. Make sense? Okay, our second one, we also start at 2 over 5, yes? My second one, though, is now 5 over 8. Can I simplify that? Nope. So that's simplest form. Everybody understand what we're doing? So you're going to do that for the other 8 values and then compare the ratios and tell me what you notice. So we'll give you guys about 5 minutes to do this. Go ahead and get started. Okay, so as we go through this one, for E, that one's now going to be 12 over 30. What can I divide those by? 6. So those of you that saw 6, you can do it in one step. If you did 2 and 3, you'd still get there. Okay? What about 6 and 15? Divide those by 3. Gives me 2/5. 8 and 20, what can I divide those by? 4. Gives me 2/5. 10 and 25, I can divide by 5. Gives me 2/5. So do you know something about the first column? Pattern. They all simplify to 2/5, meaning what? They are all equivalent. That's the definition of equivalent ratios, guys. If they simplify to the same number, they're equivalent ratios. That is our definition. On our second one, we now have 6 and 9. What can I divide those by? 3 gives me 2/3. 3 and 6, what can I divide those by? 3 gives me 1/2. 7 and 10, I can divide those by nothing, so we're done. 4 and 7, nothing. So what do we notice about the ones in Gabriel's group? They are not equivalent. Okay? So what do we notice? Ava's group are all equivalent. To 2/5. Gabriel's are not equivalent. Okay, is this making sense to you guys? You understand how to write the ratios? Are we understanding how to simplify? To determine if they're equivalent. Okay. So far it's making sense, right, Nash? Okay. Let's go to our next page then. We're on 226. We're actually going to skip this first top part. We're going to go down to the very bottom. Because we didn't actually cut out all the triangles, so we can't do the part where we're talking about them. Because you don't have them to talk about. Highlighter or marking pencil would be good. So we can represent equivalent ratios on a coordinate plane by plotting the ratio yx as the ordered pair x comma y. Here's one of your math definitions. Linear relationship is if it forms a straight line. So when you plot the points, if it forms a straight line, that is what we call a linear relationship. Ratios, by definition, will be linear relationships because they are all equivalent. Okay? So when we connect the points that represent equivalent ratios, you will form a straight line that passes through the origin. Non-equivalent ratios do not create straight lines through the origin. We're going to add a definition. Everybody go ahead and pull out your vocabulary sheet. Should be your module 2, topic 1 vocabulary. Starts with additive reasoning and multiplicative reasoning. And then go ahead and flip over to the back side. There's a huge spot on the bottom of the back. Bless you. So everybody should be on the back side of your vocabulary sheet. We're going to add another definition in. And that definition is ordered pair, because we keep using it here, but we haven't really defined it for you. So an ordered pair is the location of a point on a coordinate plane written as And this is extremely important that you write down exactly how it's written, because this will never change. For an ordered pair, we must use parentheses. My x-coordinate must come first. There must be a comma separating the two values. In a coordinate plane, there's only two possible values, and y will be your second value. The reason this is so important, this means that any mathematician in the world who looks at an ordered pair will put it in the same place, because this is a hard rule that cannot change. Okay? So you must write the ordered pair as x comma y. They also used another word here, origin, that I'm going to go ahead and add in for you guys. So if any of your classes are listening to this, you can add this on your vocabulary sheet as well. Origin. Does anybody know what origin is? 0, 0. Okay? It's where the coordinate planes cross. So where the x-axis and y-axis cross. It is given as an ordered pair of 0, 0. So when both my x and my y values are 0, that is what we call origin. It is basically the start of the coordinate plane. So origin is actually critically important when we're graphing, because anytime you're going to graph a point, you always start at origin. You'll start at origin, you'll look at your x-coordinate first, you'll go either left or right, based on if it's positive or negative. From there, you'll move up or down. Graphing is actually pretty easy once you understand it, because it never changes. It's always done exactly the same. Any questions on either of those definitions? Okay, let's go ahead and go to our next page then. Go back in your modules. We're now on page 227. So far, we've used tables, we've used double number lines to represent equivalent ratios. Now let's see how we can use a graph to determine other equivalent ratios and understand the connections between the representations. So Ava is doing rectangles that maintain the same ratio, and the table shows the lengths of the sides of the set of rectangles. So anytime you are given a table, now that we're talking about graphing, the values are actually related to x and y. If I do a table, top to bottom, the top is the x, the bottom is my y value. A lot of times you're going to see tables that are written this way, top to bottom. In this case, x is always going to be your first, y will always be your second. In the case of a double number line, x will always be the first set of data, y will always be the second set of data. Okay? When we transfer this then to the coordinate plane, and I'll give this caveat, that should always be, but apparently our book is wanting to switch up math a little bit. So pay attention to what they've done. In this case, they actually did it correctly. You can see that the x values are on the bottom. The axis that is horizontal is our x-axis. Vertical is our y-axis. For any of you that ever have trouble remembering, remember y goes mostly up and down, right? So if I look at the letter y, it tells me that's the up and down. X looks the same both ways. So that doesn't really help you, but the y will help you tell which is which. When I'm looking at either a table or a double number line, I can change my values into an ordered pair. All I have to do is add the parenthesis. I list my x value first, my comma, my y value second, and I close the parentheses. Once I've got the ordered pair, now it's easy to transfer it onto a graph. All I do is I go down to my graph. My x value is 2, so I start at origin. I go over 2, and then I pause, and then I go up because 5 is positive. I go up to 5 on that graph, and I can now place my dot. I added in this line. You guys can do the same. Let's just go ahead and take a quick pause right here. If you don't have a ruler, you're going to need one for today. So you can come back to the student desk and grab one. Okay, so now that you have your ruler, you should be able to draw that straight line just like I did on the board. What this is going to do is it allows us to make extrapolations. So our directions label the remaining ratios on each graph. So all we have to do is go to our points. So this one, we come over to 8, up to 20. This one, we go over to 10,
Stop talking, guys.
up to 25. This one, we go over to 14, up to 35. Here's what I don't like. They actually just reversed our two axes for the second one, which technically you can do, but given the way they presented the data, I don't like that they did that because you really shouldn't. But know that it is possible to do that. So basically all we've done is now are looking at our long side on the x-axis, short side on the y-axis. So now my numbers have changed. So I'm doing is basically taking all of our points off of our first one and reversing the order. So now we've got 15 to 6. We've got 20 to 8. We have 25 to 10. And we have 35 to 14. Everybody good on these?
Yes, sir.
Okay. That's all we had to do on this page. So let's go ahead and go to our next one. We're on 228. So now consider the question, what rectangle can Ava create that has a short side length of 12 units? So we've got several of them. They gave us 6 different equivalent ratios from the original graph. It shows 2 to 5, 10 to 25, 2 to 5, 14 to 35. So now we can get to 12 to 30. Here's the way this works. Again, if you draw your line in, that's why you have the rulers. Make sure you line all the points up. It should go through origin. Once you have done that, it makes it really simple. Because now I'm saying, okay, I want to know when my x value is 12, what is my y value? So I start at origin. I come over to 12. From 12, I now come up until I hit my line. Right here is where I hit my line. So I then go left, and I see that it is a value of 30. Does that make sense for you guys? At least those of you that are actually on the right page.
Like 4 years.
So she can create a rectangle that is 12 by 30. Does that make sense? Which part doesn't make sense? All of it? Do you understand that if I have the dots, I can make a line? Okay? Do you understand this is my short side because they labeled it? Do you understand this is where 12 is? Okay? From 12, all I have to do is go up until I hit my line because I know this is where the value is at 12. So then to find that value, I come to the left so that I can read it. And I can read that it is at 30. So what part didn't make sense? Good. Okay, describe how to determine the long side with a length of 16 units given each representation. So if I have my graph and I now want to find a length of 16, what do you think I'm going to do? Any guesses? Alina? Follow it up. So I'm going to go over to 16. I'm going to follow it up until I hit the line, which I need to go back up a little bit. Here's where I hit the line, yes? So then I go to the left, and I can see that I hit my line at 40. So for the graph, I go on the x-axis to 16, then go up to the line. Once you hit the line, go left to find the value of 40. Is that pretty easy to do?
Yeah.
All honest with you, guys, this is one of the biggest advantages to using a graph is making predictions. Once I have my line in place, now it's really simple because all I got to do is go over to the value I want, go up to figure out where it intersects, and I go left to figure out what that value is. Graphs make that super, super easy to make predictions. Okay? So on our next page, now I have to use a table. So let's go back 2 pages where we had the table. So all they're saying is now I need to use my table, but I need an additional value of 16. So using my table values, how would I get to 16? Sawyer? Guys, I can't even hear him. No, using the table. So how do I get to 16 using the values I've got? 4 to 16? So 4 times what? Times 4, meaning I go to the 40 and I go times 4 and I get. Is that the only option I had? No? I could have gone 8 times 2. I could have done 2 times 8. I could have done, here's a 14 and a 2, right? What's 14 plus 2? 16. But if I do additive, then I do 35 plus 5. Remember, when I do additive, I have to add the values from that row. So I could have done 14 plus 2, but then I'd done 35 plus 5, which would have given me 40. So you can see in the table, it gives you a lot more flexibility. I have a lot of different ways to look at it when I do a table. So I'm going to use the multiplicative reasoning one for my explanation. So for the table, I use multiplicative reasoning. So 4 times 4 was 16. And 10 times 4 gave me 40. Same answer, different format, and lots of different ways to do it. So Maya, it's not a helicopter. Please take it off your pencil. Thank you. Okay, here's a double number line. Now here's something I didn't hear anybody mention. How many of you noticed that that value of 12 was missing on the table?
Me.
You didn't say it.
Well, I said my mind.
No, you didn't.
I did.
Can't prove it.
You were there. How do you know?
Well,
Can't prove it.
I said he can't prove it.
you'd have to have a mind for it to actually be there. So
Sure, we can talk about it.
So here's a nice thing on the double number line. If I have gaps, it actually really stands out. So what would be between my 10 and my 14? What value would that be? Brantley? 12. So then what would be between my 25 and my 35? 30. Good job, Rashad. Does that make sense for everybody? But now it also makes it easy to extend because I know my next value after 14 is going to be 16. My next value after 35 is going to be 40. So in any of the 3 formats, I came to the same answer. I realized at 16 it's going to be 40. But I can do it in any of the 3 formats, yes? Good. Okay. One way to analyze the relationship between equivalent ratios displayed on a graph is to draw a line to connect the points. You can also extend the line to make predictions of other equivalent ratios. Sometimes all of the points on the line make sense. Other times when you draw a line, not all the points on the line make sense. We already did this, so we drew a line through all the points. Do all the points on the line you make sense in this problem? Why or why not? So if I go back to my graph, do all of the points on this line make sense for drawing a rectangle?
No.
Why not? Well, now we're back to the initial problem we had. Yes?
Does a rectangle have two sides that are even?
Okay.
Top and bottom are even. The sides and the top isn't even. But then if you look like 12 to 30, that's a square and they're all even sides. So some of them can make a rectangle, but not all. Because
Which one on this line will not make a rectangle?
30 to 12.
Yeah, it will. Just means my short sides are 12, my long sides are 30.
Oh. Never mind.
I think where you're getting confused is because of the way they set this graph up, that looks like a square, right? But you have to realize that it's the numbers that actually matter. All this is saying it's this rectangle that's 12 by 30. Okay? So don't get confused between the two. That could actually be a major problem if you're not careful on that one. Make sure you're paying attention to what is being compared. Okay? And one thing you'll notice, especially if you set the ratios up, any ratio relationship would actually look like a square if I do my actual intervals as my intervals. So this is going up by 2s, that's going up by 5s. It's different intervals because that's what my ratio was. Okay, make sense? So the bottom line on that is, oopsie, one more? No. Yes, they all can be rectangles. Now I will add a caveat. The ones that are easiest to draw are the ones that come right at intervals. But any one of those would be an equivalent ratio. Okay. How do all the representations, tables, double number lines, and graphs show equivalent ratios? How are they similar? And describe some of the advantages. I'm going to focus on this last part because I think we've gone through them all. You guys can see that they all have those ratios in there at some point. It's listed on the table. It's listed on the double number lines. It's listed on the axes of the graph. The big advantage. So if, we'll just go through the ones that they gave us. What's the big advantage of a table?
Guys, I'm coming around. If you borrow one of our rulers, please give it to me when I get your table.
What do you think? Okay, it's easier to do big jumps, right? Okay, so you can be more flexible. Easy to make big jumps. Because all I have to do is use multiplicative reasoning, and that makes those jumps really easy to make, right? What about the double number line? And the one that we just showed you pointed out a huge advantage on a double number line, right? What do the double number lines make it? What's the advantage there? Sawyer? It's easier to notice missing intervals, right? Easy to see missing intervals. And believe it or not, it's actually easier on a double number line than a table to find intervals between our numbers. So kind of two advantages on your double number line. What about for the graphs? What's the big one there? They actually pointed it out to you when they were talking about graphing them. Counter? Easier to match up, right? Okay. Easy to match the X and Y value. But what was the big advantage we saw? Clear? A lot more predictions, right? The stuff that we don't necessarily have right in the tables, but it's easy for making predictions. because I know that relationship is going to continue to infinity, as long as it's within my parameters on my graph, it's really easy to make those predictions on there. Because all I got to do is find where those values cross. So those give you some of the big advantages to each of them. It is nice to get comfortable with all three formats so that you're able to use all three of them and understand how they're related. Did you get all that written down? That was a lot of writing. It's hard to believe you're just sitting there. Okay, let's go ahead and go to our next page. I want to give you guys a chance to actually practice doing this. So I added this line on already. You guys are probably going to want to draw yours. You can just use a second pencil, or you can grab a ruler again if you need one. But here's what we're going to do. The graph shown represents the number of gallons of water used to the number of times the toilet is flushed. We need to write each point on the graph as the ratio of gallons of water used to the number of flushes. Pay attention to your directions. I'll give you that hint because I don't like that they're not being consistent in our book. What do you notice about each ratio? So in other words, do some analysis. And then we got some questions. How many gallons of water would you use if you flushed the toilet 8 times? And then how many times would you flush the toilet if you use 18 gallons? Okay? So you're going to answer those questions. And then E, did you do the same thing? We'll give you guys about 7 minutes to finish up all this page. We'll let you work together, but make sure you're focused on working, guys. So we gave you the first one. Miss McShane gave you the first one because she's too nice.
Thank you.
But our second one, again, because of the way they wrote it, we're actually starting on our y-axis. So that means it's 6 gallons to 2 flushes. Our next point is at 9 gallons to 3 flushes. And then the fourth point was at 12 gallons to 4 flushes. So if I look at all of those, what do you recognize? Anybody pick it up? Alina?
I know the gallon side, it's getting greater by 3, and the flush side is getting greater by 1.
Good. So they're all equivalent to 3 to 1.
Question.
Yes.
What if you put each ratio, you add 3 gallons and 1 flush?
That would work. That's basically the way she described it as well. But the key is understanding that it's a repeating relationship. Okay? So how many gallons of water if I flushed 8 times? In other words, if I have 8 flushes, for me, I'd go to the 4. 4 times what gives me 8? 2. So what am I going to do to the 12? Multiply by 2. So for me, explaining the method, I use multiplicative reasoning. Mostly because my graph isn't big enough. Otherwise, I just use the graph. But they kind of stopped us with the way they set it up. And I would say 4 times 2 is 8 flushes. So 12 times 2 equals 24 gallons. That's not the only way. To get to 8, I could have done 2 times 4. I could have done 1 times 8. Any of those would work. Yes, ma'am? The graph doesn't extend far enough to do it. That's one thing I don't know why they do that sometimes like this, but it is what it is. So now I've got 18 gallons. So for me, 18 gallons, I could do 6 plus my 12, right? Is that 18? So then I would do 2 plus 4 equals 6. So I can do additive reasoning. And what did I say? We started with gallons. So we said 6 plus 12 equals 18 gallons. So 2 plus 4 equals 6 flushes. Did I use the same reasoning? No, but could have I? Yes. So that one is honestly just up to you guys. Okay. The little voice in the back of the room has said we have 2 minutes left. So let's go to our homework. Page 243. This one's relatively easy, guys. Here's your big one. Please stop talking and listen. Your task is to create a graph. So you should have a graph for all of these. Do pay attention. They've already labeled the graphs for you. So make sure you set it up. Then, what is the cost for 3 pounds? What's the weight for a cost of 21? You can use the graph. You can use the tables. It doesn't ask you to tell you how you solved it, but give us some indication of what you did to solve each one, okay? Guys, please stop the chatter. Here's your key on these. Basically, that drawing the graph is for every problem, so make sure you follow through on those directions. But then answer the 2 questions that are with each one. Same thing on the back, that follows through. So you're creating the graph. You gotta create this graph. The last one is the only one that's a little different. It says consider the graph. So you can draw your line in and then answer the 2 questions that are asked.